So my name is Sagie Fisher. I'm the DFT Manager for Habana Labs. For those who are not familiar, what do we do? So we do AI chips, mainly for the cloud, very big chips. Basically, the only solution available today that is competing with NVIDIA's chips. So earlier today, we heard about the AI revolution and the capabilities of AI. So part of it, we will hear about the advantages, what challenges and things and between the generations. So what are we going to talk about today? So first of all, we will talk about the AI SOC challenges. There are some major challenges relate to those type of chips. We will discuss traditional implementation, how we did the previous generation, the solutions and what basically blocks us from progressing. Advanced implementations followed in the latest generation. And then we'll see some results comparing between traditional and advanced implementation. And finally, we'll talk about next steps, summarize the next steps. So let's start with the challenges. So what are the challenges when we're talking about AI? So the first thing is the complexity. So the AI chips are pretty big, hundreds of millimeters of silicon, but those usually are divided into different types of design. Each one of the designs we can see here, for example, compute, cache, NOC, networking, each one of those is like a chip of a different market. But here we put all of those chips into one chip. Each one of those components is basically different in the nature of the design. Now, between generations, usually in AI chips, if we'll take one generation, then the next, we don't see a slight gradual improvements. We usually see some exponential improvement. So every generation, we need to double or even more compared to the previous one. So it's not a slight improvement, it's usually a major improvement. And every major improvement comes with a major change in architecture. And this major change in architecture got to be supported. Another thing that relates to the design complexity are the IPs. So there are IPs which are usually on the cutting edge. If we're talking about HBM interfaces running up to 8 gigabit per second, we're talking about networking, which can eventually deliver 10 terabit per second in total for the number of lanes. So we're talking about many lanes, PCIe, and all kind of other IPs, which usually not necessarily developed in-house, but we can acquire those and we get those from other IP vendors. And each one of those IP vendors, they have their own way of implementing the IP, and we need to see how to integrate it with the rest of the DFT. The next thing, we're talking about design size. So as I mentioned, we talk about hundreds of millimeters, but except for that, and we talk about the sizes, so we need to route signals, we need to route the data, and usually the data we talked about HBMs, we talk about lots of data used for AI. So we talk about really wide buses, can be thousands of bits, which can run up to 2 gigahertz. So when all of that basically routed through the chip and creates all kinds of challenges. Silicon is very expensive, and we would like to take every meter of silicon and use it for better compute, so to make those chips competitive. What eventually leave us, and you can see here in this example, most of the sites are assigned for HBM or SerDeses, so we don't have DDR. So we are pretty limited in the number of GPIOs, but eventually it creates challenge when we come to test those parts, especially when we are talking about scan. Another thing is power. Those devices can reach up to 1 kilowatt functionally, okay? So even when we do DFT and we would like to test as much as possible, we will face this challenge of power management. This takes us also to test time, of course, okay? That is very challenging and something that we need to take into account. How do we keep test time under control? We talked about functional power, but we also need to take care of test power, both for wafer sort and for final test. Especially for wafer sort, needles are very, very expensive. We talk about sometimes thousands of power pins. Each one of those power pins costs a few dollars, and the test hardware can be, for example, probe card can exceed 200K. So if we accumulate all together, we understand that every implementation knob that we can do here will impact the testability, test time, and cost of the product. Test equipment. We are talking about very big devices with lots of logic and different type of logic. Testers are usually limited by the amount of memory, vector memory they have for scan. So when we come to design this chip, we need to take that into account. We would like to avoid having 2 test steps in sort, for example, just to test one part, which will double the cost and will make all the operation much more complicated. Because those are big parts, and we would like to try and get the yield as much as high as possible. Those are also usually in most advanced nodes. So we talked about different classification. How can we, as easily as possible, while running on ATE, make it easier for the test engineers to identify where do we have the defect and how to use different ill recovery options or binning capabilities. We can take to those defect classifications. Earlier here, I think Bala presented the diagnosis. So yes, in case we have failures, we would like to do that. But the first thing is how easily and fast we can detect defects and use the yield recoveries. One more thing, in system testing, those parts usually when they get into the cloud, we talk about thousands of nodes, which are part of an AI cluster. And then in this case, as you can understand, that's a huge investment, and would like to monitor and to have the capability to test those big parts in system and maybe offer some kind of repair capabilities. So those are the challenges for any generation, okay? Now let's talk about the traditional implementation, how did we tackle that? So first thing, we talk about integration. So we need to see how to control and how to drive the different components in the chip. So what we had before, we created like several blocks in the chip, which help us to drive DFT control signals to the different blocks, okay? Some type of TDRs or UDRs, which drove those blocks. All of that created massive routing across the chip, and routing, especially on those distances, more timing, more area, more buffers, something that introduced some challenges, and we had to really consider how to reduce those. The next thing are MBIST, and for the MBIST we use a kind of a parallel rings. Part of the reason for that was to help us and identify where do we have the repairs. It was not also not Tessent memory BIST, which introduced all kinds of challenges for power and for test time. The next thing is a scan, and for scan we have a very big chip. So what we needed to do is to take this chip, because we are limited in power and we are limited in the number of GPIOs. So we had to take this chip and divide it into many, many modes. For each one of the modes, we needed to generate both stacked and transition patterns. And we talk about internal mode and also test the interfaces. So all of that created a huge muxing for the scan and very complicated test program to manage and make sure that we can simulate, verify, and check all of that. More than that, we're talking about single shift clock, which needs to propagate through the entire block. So we have different distances from this GPIO, including in the scan mux, to different areas for blocks which are repeated. That's created lots of timing issues and timing challenges and sign off that we faced really late in the project, something that we could not predict and see only late in the project. And the same with the scan enable. So altogether, it's introduced, if we talk about the challenges, test time, power, sign off, all of that is hidden in the reflected on those in this scan implementation. Another thing is the hardware. How do we verify all of our implementation? So we are talking about a very big chip. Simulations were really, really long. Amount of resources needed were huge. For some of the scan modes to verify, we needed some servers with 1.5 terabyte of data. You know, something that is complicated to find and to manage. And usually it gets to the point in the project where also the functional verification needs all those resources. So we are in compete, and it needs to be managed very, very carefully. And the last thing are the pattern validation. How do we validate those patterns? How do we make sure that, because we have so many modes and we need to configure different modes and PLLs and all, how do we make sure that those patterns, and when we connect the patterns, and the test engineers connect it into the test program, we make sure that we have as less mistakes as possible, and silicon bring up will be as fast as possible. So all of that is part of traditional implementation. I guess when we are talking about small chips, all of those issues are not necessarily big problems. Okay, we don't need so many scan modes. We are less limited in GPIOs. Power is less of an issue, and simulation time is less of an issue. But here, all of those created big issues, and we understood that, as I told you, every generation it's a big leap. This solution is not scalable. We won't be able to continue and progress in our next generations and continue with it. And we understood that we need to move to a more advanced solution. So the advanced implementation that we followed in the latest project. First of all, we took the chip and we said, okay, we're doing tiling. We take and we try to break this huge chip. We said, okay, networking. Only the networking, which needs to handle 10 terabits per second and all the networking, that's a chip, okay? If you go to, I don't know, Broadcom or Vel, one of those, they have a chip that handles this amount of data, okay? Here is, as you can see, is one tile. So we said, okay, let's try and break this huge problem, okay? Divide and conquer, we're all familiar with that, but here we take it to the extreme. So we divide it into specific tiles, and we wanted to see how each one of the tiles basically is verified. So we are verifying small chips. So later on, we will try to integrate those small chips. It can save in verification resources. It saves in compute resources. We can tackle all the issues earlier as possible. That was the things that we wanted to face. When we're talking about memory based, so if it's all memory based, which is IJTAG based, we can do serial implementation. So theoretically, if we are not power limited, okay, we can run all the memories all together. This is something that can help us when we do in-system testing. Okay, we don't need to run them parallel, but we can run all the memories all together. Also, when we come to the ATE, it gives us different capabilities to if we are in wafer sort and we would like to give some granularity to the test engineers and identify where the defects, or when we are in final test and test time is more important, and we would like to test things in parallel. Verification of memory bits can be totally done in each one of the blocks and closed in each one of the tiles. So we sign off it in early stage of the project, and when we go up to the full chip, we know that this problem is already behind us. We can, in RTL, just verify that everything is working, and we save lots of simulation time in full chip. Bizer, for the repair of the bizer. This is still something that you would say, this is full chip, because eventually the bizer controller, the eFuse, all of that, this is full chip. But if we will try to load this full design into simulations, you can understand, I see how you wave your hand, it's impossible. So one of the things that we did here with the verification, and was very good feature by Tessent, is that we can use it's called bizer emulation, that you can get a gray box view of the block. So you empty the entire design, and you only have the bizer chain as a register, okay, like a shift register. So when we go to the full chip, so we can take all the blocks, basically they are empty, does not take a lot of time to simulate it, and we can take one block as a block that we have a defect to simulate it. One more thing is that we can also generate an eFuse map with the specific defects, and we can make sure that all together with the chip boot, we can simulate it and see, and we don't need the emulator, but in an emulation, but on a standard simulation environment, we can see that our boot can start the boot, perform the repair. If we would like to do in-system test, run the memory bits as part of this boot, do soft repair, predicting for any predictive defects in the field, all of that is much easier to verify. The next thing, IJTAG. So we talked about tiling. So we broke the chip into small tiles. And even before, when we did that, so today in the tool includes tiled SIBs, okay, as part of the IJTAG spec. So we started with that before it was available in the tool. We kind of mixed and match, and we broke those into tiles. That way, when we are connecting the IJTAG, and we'll see that in a minute, it's easier. It's really like a Lego, like the vision of how IJTAG should behave. When we talk about SSN, so I told you before, GPIOs is a concern. So we had several places where we had the SSN, GPIOs. What made us break the chip into several SSN buses. In this case, we had three separate SSN buses. We'll see that in a minute. And for each one of the buses, we created independent clock. So all timing sign-off could be done already at block level because of SSN as if anyone here uses SSN, so we are generating the shift clock in the block, so we can, if we had IPs with different challenges, so they had a slower shift clock, should not impact the rest of the blocks. Sign of it was at the block level and at cluster level. So once we finished cluster level simulation, SDF simulation, full chip was much, much easier. So let's talk about this IJTAG and how this integration was done, okay? So first of all, as I explained before, in the traditional, we had thousands of wires and signals routed through the chip to control. Now we said, okay, divide and conquer, each one of the blocks is totally independent. If we have IPs, not IPs, we would like to control different things. Everything, we have TDRs in the block, entire verification, RTL and SDF, we do at the block level, such that when we go to the next level, we know that everything is already verified, and the only thing that we need to do in the higher level is retargeting to make sure that the PDLs are correct. So to do this retargeting, we said we don't want to wait for the chip. So we said tiles. The tiles are usually clusters of several blocks. So at this level, again, we don't need to wait for the chip. We already verified that this block is retargetable, because if it would have been the block is retargetable to the mini chip or the cluster that it is, we know that once we get to the full chip, the only thing we will need to take care of is that all those IJTAG connections are well connected. So how those, and those are the clusters. So we verified all the verification done at cluster level, and then the retargeting done at cluster level. The clusters themselves are connected to one another. So it's like a Lego. When we define those clusters, and you see those drawings, so the IJTAG network, Chris here kind of helped us with that. So he smiles, and he's not smiling for no reason. The IJTAG network here was very, very complex, okay? So we had some blocks or clusters. So for example, if you can see here in the middle, we had some blocks that we had 4 or 5 different IJTAG passes. And we wanted all of that to be inside the blocks. So to make that, yes, we had to specify that. But then when it was specified correctly at the block level, we could verify the clusters. And then each one of the clusters, eventually, we tried to make it one input and one output, such that when we go to the full chip, as you saw in this animation, it was just plug and play together, and verification was easier when we got to the higher level, and we only need to verify the network connectivity. Another thing which helped, and our backend team, implementations team, were very thankful to us. All of that, yes, we took a little bit extra work to define all of that inside the blocks and inside the cluster. So all the signals, SSN, Bizer, IJTAG, everything fit through within the blocks. So we had to define it correctly. But then when we got to the higher level, they didn't see new timing passes. Everything was already signed off at the lower level. So that saved lots of time when we are looking at full chip timing. And full chip timing for such a big chips, that's a huge challenge for runtime and issues which need to be found. And the chip itself, because how it's built, it's not the fact that you see it's separated. So we created several rings, which were physically and also took into account. Over here, I could not show that, but we had, for example, different clusters who came in different orientations. So one time it was implemented top to bottom, and the other time it was bottom to top, all kind of flips, right to left, left to right, and forward. But all of that should have been reflected in the single implementation of the IJTAG, and then we met all of that in full chip. So once you do the architecture correctly at block level and cluster level, and you can verify that in cluster level, when we got to the full chip, everything was ran much faster and easier. SSN. So SSN was a challenge as well. Okay, we want to run it fast. We want to make sure that we verify everything at block level. As I said, we have sometimes blocks which are very, very long, so meaning the SSN should travel tens of millimeters, okay? That's the order of magnitude. And we wanted to make sure that timing that we sign off, once we reach ATE and we'll get to ATE, we will be able to run it as fast as possible, basically, okay? That we won't face new issues. So first of all, we created the bus based on the GPIO groups. So we had 3 groups of GPIOs. So each one of the groups had SSN bus with its own clock and everything, okay? One more thing that we made sure that inside the blocks, and if we had like long channel blocks, so we took extra guard band, is to add enough pipelines, SSN pipelines on the bus. All of that really helped to make sure that once we signed off the timing at block level, when we went up from block to cluster and from cluster to chip, we basically didn't met any timing issue. So this is something that now when we are moving to our next project, it's give our, compared to the traditional implementation that timing sign off, we get to the full chip, we found issues, we had to go back to the block and do those back and forth. So here we know that if we will do good work at block level, and this is easy, block is small, okay? Once we go to the full chip, it should be much, much easier for us. One more thing is that we try to take identical blocks to make identical blocks on the same bus. This says when we are talking about pattern count, tester memory, power, all of that, this is something that helps us to manage it much better. So if I created some drawing just to explain how it looks. So those SSN buses, so here like the IJTAG, we had some blocks where we had all kind of directions for the SSN bus, okay? Sometimes we had 3 or 4 directions of SSN bus go in and out to the block. All of that had to be described and had to be pipelined. But again, it's a small Lego pieces, and once we connected all this Lego, all of that worked unbelievably good. You can see that, for example, we see examples of those buses here. Depends on the GPIO's locations. So we put it all together. We try to make sure that we are keeping the loop timings relates to the SSN bus and the SSN clock. So we took care of that, and it's helped us. One more thing is on-chip compare. So the on-chip compare for all those identical blocks, and we have some blocks with more than 200 instances available in the chip. So we have those on-chip compare. What it basically gives us is that when we go to production and we work with the test engineers, they run a test with 200 instances of the same block, and always on-chip compare. So tester memory is very low, and they just need to read the JTAG as part of the SSN, and they know which one of the blocks failed and how to handle it from this point. So that made the interface between the DFT implementation, the test engineers, and the test program much easier, okay? Retargeting. So we know that retargeting sometimes can be an issue. We define the signals, we didn't define the signals. We have a clock. Because it's all clusters, we could do this retargeting already at cluster level. We made sure that each cluster is a small chip. When we got to the full chip, again, the only thing that we had to verify was that the SSN bus itself really connects as we planned, and to run retargeting options includes PLL configurations, which at block level or cluster level are like forces. Make sure that we define that and continue from here. External mode, also, we could already close that at cluster level, make sure that all the configurations, all the clock, everything is under control. What we try to do here, as you can understand from what I say, we try to take all the verifications on the implementation, do shift left, make it as earlier as possible, not leave as much as possible to the full chip. So the full chip became manual integration task. Of course, the last thing for the external mode was patterns had to be generated from full chip, okay? That's a longer process, but it was with very high confidence because everything was verified already, okay? Both stacked and transition simulations. We had a few full chip interfaces which check only in full chip, but also timing-wise, SDF, we could simulate all of those. 95% were already signed off at the cluster level, saved us a lot of time. And for the PDLs, as part of this retargeting, if it's specific IPs, special IPs, or needed special PDLs, we verified it block cluster, and we come to the full chip. Again, pretty easy. So what were the efforts to get to this point? Okay, so as you can understand, we start from very old implementation, okay? And we, in one project, we implemented many things all together. If it's a all SSN, IJTAG, in-system test, all of it in one project. So what was needed? So the first thing was that we tried to do as much as possible in RTL. Insert all the logic that is needed and hold the hardware already in RTL, so we could verify that. So all this verification for block, for cluster, and full chip done in RTL. So if I run IJTAG simulation with a gray box at full chip, despite that a huge chip, but it's IJTAG gray box, so I can load the entire chip and run the simulation in a reasonable time. The same for the Bizer, as I explained, and the same for SSN. So it really saved us and helped us to find most of the issues early in the project. Another thing about the SDF, so we didn't just use SDC, the SDC and SDF simulations at block level, but when we did, for example, the retargeting, the cluster, we did retargeting, okay? We created the equal view for this cluster and we did the extraction. So we extracted a full SDC. This full SDC also not included just the constraints for the IJTA clock or the SSN connectivity, but we also retargeted any special constraints exist in the block. For example, for the memory beast, we took it to the next level. This helps when we talk about this big chip to take all those constraints and for our backend team to make sure that if we talk about signal integrity of the clock or noise or anything like that, all of that is taken into account, represented correctly, because usually the memory beast hardware is not part of the standard SDC which is generated on the higher level. So here we took it into account, and it's I'll try to make it faster. And then SDF was cleaner for stitching. Here we faced all kinds of special issues, especially with the old flow. So we did, despite our backend team use FC's Fusion compiler by Synopsys, the stitching died by Tessent. It gave us lots of power. First of all, we created the in-house algorithm to do physical aware scan stitching, which apparently is better than what Fusion is doing. So we managed to do something than Synopsys, don't tell them that. And it gave us the capability to maintain test modes. It gave us the capability to control chains. We saw some issues with wrapper chains. So here we could use different types of Tessent wrapper cells and manage different wrapper cells for high speed and low speed ports. So it gave us lots of power to do things. Now, for example, we're also adding LOS on top of that, and it's all integrated. So it gives us lots of power and lots of control in hand that we have using this Tessent stitching. Okay, that's a very powerful tool that we have in hand. And for gate level, we made sure that internal mode, external mode, again, we start at low level and we go to the higher level. So you would think that all of these projects, okay, and do such a big change should require lots of time and lots of efforts. So from time perspective, I can tell you that for the first time in Habana, DFT was not the critical point to tape out, okay? So I think that's made, at the beginning when I said everyone, when I told my managers we are going to do this change, they were kind of afraid. You would agree with them, right? Do such a big change, such a big project, very important. But for the first time, DFT was not, and we made it. We started very structurally from RTL, level after level. We made sure that we can verify all. So once we verified all in the early stage, when we get to the later stages, simulations were shortened. We didn't have a constraint with the functional verification to use the strong servers, and everything was done much faster. Also, pattern generation was not an issue. From a headcount point of view, we would think that we will have, I don't know, 40 people or 50 people. No. When we started this project, I think that I'm the only one who was familiar with Tessent, okay, in my team. Just to people probably won't believe that, okay? But in total, we were 8 engineers who ramp up all this flow. Yes, just to show if you work correctly with the tool, how powerful it is. Okay, most of them use Tessent for the first time, and to understand what is IJTAG, what is SSN, how do we targeting, all of that all together. And I think that now each one of them is an expert. Okay, after doing that. Yes, this is why yes, we are hiding them. Yes. So let's talk about results. Till now it was nice, but let's talk about results. So first about verification, I told you that again, it's important to mention that the numbers here are normalized for chip and gate count. This generation is, as I said at the beginning of the presentation, every generation it's more than double. So we're talking about a huge amount of silicon area, gate count. You know, it's not just a more advanced node. Silicon is also bigger, so it's they're multiply, okay? So, but eventually, if we look at the verification time, so scan was much faster, memory bit was faster, chip control was way much faster because we could verify everything already at the block level, okay? And the IPs also, we could verify the IPs already at block level, and then when we got to the full chip, it was just retargeting. Sometimes we had some issues with clocks, someone who didn't follow the right clock connectivity, but it was easy to find because we knew that it's already passed at block level. When we talk about compute resources, so I told you that before we had to use massive servers and with a lot of CPUs, lots of memory. So here, because everything done earlier, so despite we had more silicon, we used less resources, okay? So that was a very important thing. When we talk about test time, so I told you test time is a big issue. So I think here, by running more than 200 cores, for example, under one mode, and basically we understood, and I'll talk about the power in a minute, we can run even more, okay? So this, about 10% of the test time, okay? 10% compared to the original. That's something that our test engineers could not believe, okay? No one took it into account. And you know, when I said we will be there, I put my head on the table, basically gambling on that. When I saw that all of that worked, I said, we did a good job. But yes, and we can do it even faster, but part of the reason that we don't push it even more is we don't want to make the test program more complex, okay? But yes, test time right now is unbelievably faster, both for scan and for memory boost. When we talk about tester memory, so here, again, because we have this on-chip compare, so we can squeeze the tester memory. So before that, for the previous project, we had to do lots of planning. How do we assign the channels, scan channels, and how do we, inside the tester, do memory pooling? Okay, it's within the tester, you can pull memory from one channel to another. A lot of engineering, which involve very complex cross platforms, and we had to discuss with Advantest on that. Over here, suddenly we see that no, we are good. We don't have problem. That's became a non-issue for scan and for memory boost. For power, thanks to SSN. So previously, one of the things that limited us is the power, because everyone gets the clock, gets the scan enable all together. So we see a big jumps in power. So now, because of the SSN, each unit is independent, and if you manage correctly the bus, so each one of the blocks kind of work independently, and the edges of the clocks are unaligned, such that when they ran the pattern, and I asked them to measure the power, I told you, are you sure that the pattern is even working? We had to take and change bits in the patterns and to make sure that it's really failing when we got the first silicon, because the power is so low. This is what also gave us the confidence and allowed us to generate those patterns. Initially, we started initial patterns without lots of blocks running together, but when we saw that the power is so low, it gave us the option to use the power of the on-chip compare and run so many blocks all together and eventually save test time. Memory boost, that's a little bit more, but the reason for that is that we just run things faster and more in parallel. Just a second. Yes, we talked about this part. Okay, so about the next steps. So when we moved to Tessent, and we used all the advanced features by Tessent, and I think that I try to think which one of if we go on the checkbox, which one we missed, and I doubt that we missed one. I don't know, Itamar, correct me if I'm wrong. So it really gave us even the beta of the beta, yes. We left something for the next project. Yes. Yeah. Yeah, even logic based. Yes. So first of all, it's let us create a flow which is really robust and allowed us to move to the next generation. So right now, while working on the next generation, again, everything more than doubles and ex- exponentially everything become bigger. We know that we have a flow that is robust enough, and the DFT team are the last tenth team in Habana right now. Okay, so people have life. That's an important thing. Second of all, the second point is that the effort, as I showed you, sometimes people afraid to do this change. Yes, change is something that, as human being, we're afraid. But here, I can tell you, this change you should not be afraid about. Production cost, we saw the benefit by test time, by tester memory, allowed us also for the future generation not think about moving to a more complex and expensive tester. So this is something that is well noticeable and also give us the flexibility. We saved a lot of resources from the backend team because timing can do early. Okay, so that's also very, very something that is good for the company. Tessent allowed us to build automation such that today, even when we plug new people into the team, it's become easier for them to take 90% of the blocks and run it. You don't need the deep knowledge because of the automation that was built, but we can take the flow. We make sure that people are not just button pushers, but everyone still works on all kind of flow enhancement and implement new capabilities into the flow. One of the things that we noticed, and maybe that's our problem because of the size of the chip, and it's something that we work on those days, some optimizations to better use the SSN bus, taking into account shift speed, SSN speed, EDT number of channels, if with on-chip compare, without on-chip compare, such that we can fully optimize and utilize, okay, the capabilities SSN gives us together with the tester limitations. So this is something, a model that we are working on those days, and it we believe that it's give us the extra flavor for jump. Yes. Yes.